Hi, everyone. Thanks for having me. I will discuss how photoevaporation affects our vision of clouds and especially of photodissociation regions. Let us start with a bit of context. As you know, stars form in interstellar clouds by the gravitational collapse of the gas. The newborn star will then apply a feedback on its parent cloud through stellar winds and radiation that will illuminate and shape the cloud, like the famous Great Bar of the Orion Nebula. This stellar feedback represents an input of energy that will excite chemical species that we can then observe through the line emission. The numerous observed lines are used as constraints to deduce the physical properties of the clouds and constrain the stellar feedback. This question is fundamental for extragalactic studies in order to better understand the star formation rate and galactic evolution. It is up to us to grasp as well as possible how our neighbor clouds work to better model unresolved clouds from other galaxies. Our local clouds, as well as clouds from other galaxies, are surrounded by a thin interface where the gas reprocesses the stellar radiation. This region is exposed to UV photons that are able to dissociate molecular hydrogen. It is why this region is named the photodissociation region, or PDR. On this schematic view, we have the stars on the far left. They emit radiations that create an ionized region. The ionizing radiation is absorbed and the gas becomes neutral at the ionization front. We enter now the atomic region. The same logic applies here to dissociating radiation, and molecular hydrogen becomes dominant at the dissociation front. We then enter the molecular region, which is the matter reservoir in which the stars form. The vision of PDRs that I just showed you has been the classic interpretation of observations since, let's say, the 90s. But because the observations are more and more precise each year, our models must evolve to adapt to new standards set by those observations. In the last years, especially, we have been witness of a change of vision of PDR structures. For example, Herschel allowed Javier Goicoechea to notice that in the Orion molecular cloud, the CH+ molecular ion, in white contours here, was tracing the strongly irradiated gas. And on the figure, we can indeed see that it is concentrated in the regions where the radiation field intensity is the highest, in green and black on the figure, around the trapezium cluster and at the Orion bar. Even thinner observations made with ALMA allowed to understand that SH+, which has a similar behavior to CH+, was not only found in regions of intense irradiation, but more specifically in a thin layer that coincides with the H2 dissociation front. To produce CH+ or SH+, you need very hot gas, so they should not be abundant at the dissociation front, but energy can directly be provided by H2 molecules. Indeed, at the dissociation front, the UV pumping and fluorescence are very efficient processes, allowing an H2 molecule to reach high excitation in the revibrational ladder in red here. An excitation of V = 2 suffices to cross the activation barrier to create both a CH+ and a CH+. Additionally, the formation of CH+ unlocks a chain of reactions producing rotationally excited CO, and Herschel indeed confirms the observation in the Orion bar of many CO lines, reaching a rotational number of 23. Christine Jobelin, in a paper of 2018, found that isobaric models work quite well to reproduce those CO observations here. By doing so, they found a high thermal pressure structure in the Orion bar. And this kind of structure, a thin high pressure layer surrounded by lower pressure layers, can only be maintained dynamically. So a high pressure is found in the Orion bar, but the same results were found in NGC 1723 or in M17. In Jobelin 2018, they found on this figure that there is a strong correlation between the intensity of the radiation field and the PDR pressures, suggesting that there is a physical mechanism linking the two. An explanation that replicates both the high pressures and the correlation was proposed by Emmerich Bon, which is called the photoevaporation mechanism. This phenomenon has been known for a while now, but the instruments did not allow to highlight its effects until now. So The photoevaporation consists in the high-speed evaporation of heated ionized gas through the ionization front. By the rocket effect, the pressure increases in the other direction inside the cloud. And it is this mechanism that produces the high pressures found in PDRs. With the evaporation of the gas, the ionization front will advance in the neutral gas. And if we place ourselves in the frame of reference of the ionization front, then this propagation translates into advection of the gas through the front. This advection should reduce the width of the atomic region by maintaining its chemistry out of equilibrium, thus impacting most of the usual tracers. So we just saw that photoevaporation should impact the atomic region and the transition from H to H2. Sternberg 2014 developed an analytical theory of the H-H2 transition, and he quantified how much atomic hydrogen there is at the edge of a cloud by computing its total column density. And this formula depends on the physical conditions, such as the gas density or the radiation field intensity. This kind of study is widely used today to assess the atomic and molecular mass fractions. Indeed, the mass fraction of H2 is linked to the star formation rate by the Schmidt-Kennicut relation. So the Sternberg analytical study, similarly to most of the numerical codes modeling PDRs, make the hypothesis of a static and stationary gas. But we saw that to reach the high pressures observed required to take into account a fundamentally dynamical process, which is the photoevaporation. As a consequence, we must update the model of the H-H2 transition by including the dynamical effects, and that was the purpose of the paper that I will now introduce. So we have built a dedicated semi-analytical model based on two physical parameters. The first of which is the ratio between the intensity of the UV radiation field G node and NH, the gas proton density. The other parameter is VIF, the velocity of the ionization front, which is the advection velocity of the gas. We thus consider the top equation where the density of H2 is supposed stationary in the left-hand side, and in the right-hand side, H2 forms on dust grains and is destroyed by UV photons. Consider for now that there is no advection yet in a static case. There, the resolution of this equation gives us the density profile of H and H2 as functions of the depth in the cloud. The radiation comes from the left, so that hydrogen is mainly atomic at the edge and becomes molecular to the right. The H-H2 transition is defined where the abundances cross each other. So now we add the advection term in the top equilibrium equation of H2, and this advection plays from right to left, so from the H2 reservoir in the core to the edge, and it thus acts like a formation term for H2. And as a consequence, we see on the figure that the transition is shifted to the left. The more we increase the advection velocity, the closer the transition gets to the ionization front. And if the advection dominates, then the transition is pushed against the ionization front, so that the two now form a merged structure. In this case, the atomic region does not exist, and this behavior was first found by Bertoldi and Drain in 1996. But a question arises. What are the physical conditions that verify this merging? We have thus explored the space parameter of the G0 over NH ratio on the y-axis and the velocity of the ionization front on the x-axis. For each couple of values, we look if the fronts are merged or not, and it gives us this map. For the fronts to be merged, the conditions must be to the right of the orange line, and to its left, the fronts are dissociated. Other merging criterion were found in the past by Bertoldi and Drain in 1996 and by Sturzer and Hollenbach in 1998. They are the straight black lines. Our criterion is curved because we took into account an H2 self-shielding function. This curvature is very important because thanks to it, it is easier for PDRs with low G0 over NH to have merged fronts. We now superimpose the physical conditions of known PDRs, such as the Horsed or the iron bar, as the blue crosses. The values attributed to each PDR were derived from estimates of physical parameters, such as the density in the PDR, but also in the adjacent H2 region. It seems that two groups appear. On the top right of the figure, we have the highly excited PDRs, which velocity of ionization front seem limited, saturated to the red vertical line. And it actually is a limit well known since the 60s in the ionization front theory. So this behavior was expected. Okay, to the bottom left, we have the weakly excited PDRs that, despite their error bars, seem to align on the front merging criterion, as if this latter also played a saturation role. It could be a consequence of the fact that the ionization front cannot propagate faster than the dissociation front. Being this close to the front merging criterion, we in fact expect that it is the weakly excited PDRs that should display the strongest dynamical effects. For highly excited PDRs, the dynamical effects are moderated but non-negligible. To sum up this, in this paper published last year, we extended the study of the HI-to-H2 transition by including the propagation of the ionization front. This propagation brings the HI-to-H2 transition closer to the ionization front and reduces the width of the atomic region. Under some conditions, the front can even merge in a scenario where the atomic region no longer exists. With the reduction or disappearance of the atomic region, the total column density of hydrogen, of atomic hydrogen, is reduced compared to static models. So we obtain at the bottom of the slide a set of equations to quickly compute the said column density for any set of physical conditions, including metallicity. By comparing the front merging criterion to observations, we discovered that PDRs should be subject to strong dynamical effects, especially in the case of weakly excited PDRs, such as the Horsehead Nebula. To compare our theory to observations, we need to find markers of the dynamics. And this job is very much suited for the GWST. Given its high spatial resolution, it will bring insight on the PDR structures by allowing to constrain the size of the atomic region. And moreover, its spectrometers will observe many H2 vibrational lines in which we will be able to look for dynamical markers. And to prepare for the release of the fully calibrated spectrums of the James Webb, we confronted quantitatively our models to existing observations made with the IGRINS spectrograph last year. They found 170 H2 emission lines in 6 PDRs, reaching a vibrational number of 14. And let us have a quick look at the observations by taking, again, the example of the Orion bar, in which they found 108 lines. On the figure here, the emission lines are separated regarding the vibrational number of the upper level. We tried to compare those observations to static and stationary models to see if there were any discrepancies between the two. And what we found was this. An isobaric model using the Meudon PDR code reproduces very well the observations, but it requires to include a lot of microphysical processes, such as the description of UV pumping, the fluorescence, the infrared cascade, or the collisions. And I take a few seconds to mention that this success would not be possible if not for the inclusion of the collision rates determined by the LUPM group. Indeed, here we compare two models, one with the new rates in solid lines, and one with the previous rates in dashed lines. And the fact that we included the new collision rates that go high enough in the vibrational ladder allowed to discover the presence of a collisional cascade that brings population from the higher vibrational states down to lower vibrational states. In the Orion bar, thanks to its high density, the cascade that follows UV pumping and fluorescence is mainly collisional instead of radiative. So to conclude, the first paper allowed to better quantify how photoevaporation and the propagation of the ionization front impact the atomic region and the HI-to-H2 transition. Those effects are expected to show up in GWST observations. That is why we prepared, on the one hand, by studying high-resolution ALMA observations of the Horsehead that are not out yet, and on the other hand, by looking into IGRINS observations of H2 raw vibrational lines, from which we deduced that it is not in the lines excited by UV pumping that we should look for dynamic, but actually in lines excited by collision, such as the pure rotational lines of H2 that are known to be hard to reproduce in the Horsehead, for example. We also implemented the solving of H2 excitation in the dynamical PDR code called Hydra. That's it. Thank you.